Let's do a tour de force with this linear system and learn as much as we can about it in every way we've been thinking about these things all at once. So you really want to concentrate. We're going to put all of our ideas together, including the ideas related to change of coordinates, which I haven't really emphasized in full depth in the lectures yet. So it's a system of linear equations, both in scalar form and in matrix form. To find the general solution, you want to find the eigenvalues and the eigenvectors. You create the matrix A minus lambda I and take its determinant and find the roots of that polynomial. Why, you might ask? Well, that's discussed in the lectures. The motivation for this is related to the straight line solutions. That's where these ideas come from. You're looking for points in the plane where the output of the vector field is parallel to the position vector for the point. In other words, like if you imagine a point right there, say, is that point's position vector and the output of the vector field parallel? Sometimes it is, okay? And in the special case when it is, that's going to correspond to straight line solutions. So that arrow is supposed to represent the position vector of a point. And if you attach a vector in the vector field to it that happens to be parallel, pointing in the same direction, not necessarily the same length, and not necessarily pointing in the same direction, it could point in the opposite direction, but it's parallel, then that would be a situation where the vector field, represented as A times V, say, is a scalar multiple of V. Lambda times V. A times V is the output of the vector field. Lambda times V is a scalar times V, a scalar multiple of V. This equation is saying the output of the vector field is parallel to the position vector. That's it. An algebraic way of describing a geometric reality. And then essentially what you do is you rearrange this equation, AV equals lambda V, which is the definition of what it means for V to be an eigenvector and lambda to be a corresponding eigenvalue, and rearrange it as AV minus lambda V equals the zero vector, and then factor out the V like this. And you're looking for non-zero solutions for that. You want to find vectors V that are non-zero that solve this equation. Well, the only way that's going to happen is if this matrix is what's called singular, which means non-invertible, which means its determinant is zero. That's why you set the determinant of this matrix equal to zero, ultimately, set this equal to zero, and solve for lambda to find the possible values of lambda that give you non-zero solutions of this equation. Non-trivial null spaces of this matrix. Non-trivial kernels of the corresponding linear transformation. It's all connected. When you solve such a system by plugging in those values of lambda, in this case, -3 and -2, you will get a system that has non-zero solutions. You will get free variables. I'm not even bothering to go to RREF here. I can see these two rows are scalar multiples of each other. They both represent the equation essentially x minus y equals 0. In other words, x equals y. If you want to think of y as a free variable, then x equals y. So any scalar multiple of this vector, 1, 1, would be a solution. It's always tricky to remember. You got to bring these things over to the other side of the equation. So even though you see a minus sign there, you don't see any minus signs there. You got to imagine bringing it over to the other side of the equation. So you should have gotten an eigenvector lambda -3 corresponding to an eigenvalue of -3 corresponding to an eigenvector of 1, 1. For the other eigenvalue, -2, the corresponding eigenvector is 2, 1. Replace lambda with -2. Both here and here, you get a matrix, a coefficient matrix, where the two rows are multiples of each other. In fact, they're the exact same row in this case. And they correspond to the equation x minus 2y equals 0. So x is 2y. If y is a free variable and you say let it equal 1, then x is forced to be 2. But these eigenvectors are not unique. Eigenvalues are unique, okay? These are the only two eigenvalues. But eigenvectors are not unique. you could use any non-zero scalar multiples of these things and get another eigenvector. Okay, but I just always try to pick the simplest ones I can think of. Don't pick 0, 0 though. The 0 vector is not an eigenvector. These do then help you find the general solution and also help you draw the phase plane. Let's talk about that next. So the general solution, you take a linear combination of e to the lambda 1 times t times its eigenvector and e to the lambda 2 times t times its eigenvector. K1 and K2 are arbitrary constants. I started making a C there. That's why it looks a little funny. This is related still to vector space theory. Ideas of basis and dimension. These two functions are both individually solutions of the system, and they're linearly independent. They're not scalar multiples of each other. Being a two-dimensional system, it's possible to show that the solution space is a two-dimensional vector space. And therefore, these two functions, emphasis on the word function, form a basis for the solution space. And so if I take a linear combination of them, that's guaranteed to be the general solution. All that vector space theory is behind the scenes here in writing this general solution. The dimension of the solution space is two-dimensional. So any two linearly independent solutions will be a basis. And therefore, an arbitrary linear combination of them will be a general solution. But again, the V's themselves are not unique. Let's draw the phase plane. Started drawing it here with nullclines to help. The x nullcline, I set dx dt equal to 0. That's a line through the origin with a slope of -1/2. The y nullcline, I set the dy dt equation equal to 0. That's a line through the origin with a slope of +1/4. These nullclines can be used with linear systems. The textbook doesn't do it because it waits till chapter 5. I think it's good to introduce early. In chapter 5, we still apply nullclines to nonlinear systems. It's even more useful there. Here are the nullclines. This one's the x nullcline, so you cross it vertically. This one's the y nullcline, so you solutions cross horizontally. We can also, I haven't done so yet, draw on the straight line solutions based on this being your general solution. The straight line solutions are parallel to the eigenvectors, 1, 1, and 2, 1. And they both have negative eigenvalues, so as t goes to infinity, solutions head toward 0. The solution curves head toward the origin. It's going to be a sink in the phase plane. Parallel to 1, 1 and parallel to 2, 1. One straight line solution parallel to 1, 1 is going to be along that line. That's the line y equals x. It's not a nullcline. It's a straight line solution. Draw arrows going toward the origin. Another one is parallel to the vector 2, 1, which has a slope of 1/2, about like this. Once again, the eigenvalues are negative, so the solutions head toward the origin. Now you take this information and do your best to draw the phase plane, the phase portrait, all the other solutions. You can also think about the signs. Where are these quantities positive and where are they negative? I mean, if we start down here, over here, where x is positive and y is 0, say, we're on the x-axis to start with, say. If x is positive and y is 0, dx dt is negative and dy dt is positive. Solutions have to go to the northwest. dx dt is negative, dy dt is positive. So they got to head this way. They got to cross this y nullcline with a horizontal tangent. And then they're in this region up here where I bet it's going to go, looking at the picture here, to the southwest and head toward the origin. If I want to double check, do solutions in this region go to the southwest? Are both dx dt and dy dt negative? Pick a point up here where x is 0 and y is positive. Both of these are going to be negative when x is 0 and y is positive. All solutions in this region up here between these nullclines got to go to the southwest. I mean, I can see the straight line solutions as well go to the southwest. If I started with an initial condition down here, for consistency's sake, I hope it's pretty intuitive. It's got to go up this way to the northeast, cross this x nullcline with a vertical tangent, then go to the northwest. Is it going to cross that y nullcline before it heads toward the origin? Yes, it will. It will not head toward the origin without crossing that y nullcline. I mean, it's going to be very close to the origin before it crosses. I know it can't. I know it's got to cross that other nullcline, because if it didn't, if it just stayed in this region here, there'd have to be another straight line solution in there, and there's not. Because these solutions end up being tangent to straight line solutions. Question?
I have a question. The straight line solutions, they're going in towards the origin.
Yep.
What do answers between those straight line solutions look like? Do they kind of start by hugging the straight line solutions, then kind of go toward the middle of the straight line solutions, or?
So are you talking about with initial conditions in here, say?
Yeah.
Yeah. Okay. Let's be careful. That's a good point. Let me draw some other ones first, and then we'll come back to your point.
Okay.
Probably the easiest ones to draw are similar, sort of the opposite across the origin from these. Like you could have one here going this way and tangent, it seems, to this straight line solution. If you start up here, it's going to go down this way. And yes, I know it's got to cross this green line here before it goes toward the origin, because there are no other straight line solutions in there. And yeah, what happens if you have an initial condition here or here? I claim all solutions except along the line y equals x have to be tangent to this straight line solution. So I claim if you start up here, you got to go this way and be tangent to this one. You start down here, you got to go this way and be tangent to the same line, actually, on the other side of the origin. The only solutions that are not tangent to this red line with a slope of 1/2 are the solutions on the straight line solution with a slope of 1. Those are the only solutions that are not tangent to that. What's the intuition behind that? This is a very subtle point, but important. This straight line solution, y equals x, by the way, that's not the equation of the straight line solution itself. That's just the line it lies on. The equation of the straight line solution itself is essentially just that expression as a parametric curve. That corresponds to the eigenvalue -3. This was lambda 1 equals -3. The other straight line solution corresponds to the eigenvalue -2. Lambda 2 equals -2. Here's the quick way to know which line of eigenvectors most solution curves are tangent to as t goes to infinity. It's whichever one corresponds to the eigenvalue closer to 0. -2 is closer to 0 than -3 is. And so I'm just telling you, based on that, that's why this line is the line that most solutions are tangent to as t goes to infinity. But why? What's the intuition? The intuition there is because -3 being further away from 0 corresponds to an exponential decay that's faster. You look at these two functions here, which decays to 0 faster as t goes to infinity? That one does, with the eigenvalue further away from 0. So the decay to 0 is faster in this term than it is in this one. So intuitively, sort of in this direction, corresponding to this line, the component of solutions in that new axis skewed axis direction has to go to 0 faster than in this direction. And if you think about it, that means the solution's got to be tangent to this one, because when you're tangent to this one, their components relative to this skewed axis are a lot closer to 0. When you're there, say, right there, on this solution curve right about there, say, if you think about the skewed coordinate axes, you're a lot closer to this red line than you are to this red line. Meaning the coordinate of this point in the skewed coordinate system with respect to this line is a lot closer to 0 than the coordinate with respect to this red line. That's a very vague description of what's really a very algebraic idea. Not expecting that you're going to necessarily remember what I just said there, so you got to think about it after class. The book actually gives a more rigorous explanation of it using limits. I don't want to go there. What I think would be most worthwhile for our last 12 minutes here is to try to relate this to flows and coordinate changes as quickly as we can in 12 minutes here. Let's relate it to coordinate changes first, actually. So in the lectures, I don't really go here quite yet. I'm previewing what starts really in lecture 24B, which is right before the exam, but comes into full fruition after exam 3. But it's still related to things that you do need to know for exam 3. It's related to change of coordinates matrices and bases. It's related to all that. And what I mentioned last Friday. If you create a matrix P whose columns are the eigenvectors. What were the eigenvectors? 1, 1, and 2, 1. You have created a matrix that's first of all invertible because those columns are basis vectors for R2. They are linearly independent. This is invertible. I made this determinant the opposite of the example from last Friday. The determinant of this one's -1 instead of +1, but that's still okay. Here's the inverse matrix. I swap the numbers on the main diagonal. Well, they're both 1s, so it still stays both 1s. And I negated the numbers on the off diagonal, and I multiplied by 1 over the determinant. And this is just a -1. Multiply the -1 through, you get -1, +2, +1, -1. This is P inverse, if I didn't make a mistake. You can check it. I claim if I calculate P inverse times AP, I get a diagonal matrix. Let's see if that happens. Let's do a quick calculation. A was this matrix. P inverse AP. Doing this calculation as quick as I can here. Taking dot products, I get a -1 minus 2 is -3. -2 minus 2 is -4. Hopefully I don't make a mistake. 1 minus 4 is -3. 2 minus 4 is -2. What are they doing? Here I get +3 times -6 is -3. I bet I get a 0 up here. Let's see. +4 times -4 is 0. I bet I get a 0 down here. -3 times plus +3 is 0. I bet I get -2 here. -4 plus 2 is -2. How did I know that would happen? Because those are the eigenvalues. I knew that had to be the case if I didn't make a mistake. That's a diagonal matrix. Call it D. What did we do last Friday? Last Friday, we reversed this process. I started with a diagonal matrix. You did a completely decoupled system. And I told you what P was, and you found an A that had the same eigenvalues. That's exactly what we did here in reverse. This matrix P is a change of coordinates matrix that converts our original linear system to a completely decoupled system. In the new coordinate system, which corresponds to these lines, the straight line solutions being a skewed coordinate system, the system is completely decoupled and very easy to solve. In particular, the matrix exponential is very easy to solve for. E to the TD is also a diagonal matrix looking like this. And it then turns out that E to the TA, since P inverse AP is D, it turns out that D is PA P inverse. Oops. No, sorry. A is PD P inverse. Easy to get confused there. And it turns out, without explaining this, this means the matrix exponential E to the TA turns out to equal P times E to the TD times P inverse. This is a super useful thing, allowing you to compute the matrix exponential of A using the diagonal matrix D, whose matrix exponential we can find very easily. So far with matrix exponentials, we're only using technology. Here's the key to doing it by hand. How is this related to flows? Remember the beautiful generalization. dy dt equals a times y. Y of 0 equals y sub 0. That is a generic initial value problem. It's got unique solution, not general solution, unique solution. Y equals, I'll go ahead and use phi, capital phi, sub y0 of t equals, I wrote e to the at last time, I'll write e to the ta this time. That's actually more how I do it in the lectures. What this means is if you can find this matrix exponential, you can solve the system. You can also relate it to flows. That thing you find with Mathematica. But we also could do it now this way too and get the same answer. The flow, I'll go to using a curvy phi here, has the same formula. The exact same formula, we're just thinking of it differently. The time one map, you just replace t with 1 and you get this. And this, then you think of as generating a difference equation, not a differential equation, a difference equation. Yn equals ultimately e to the a times y sub n minus 1. And these two things are equal. Oops, yeah, okay, that's the difference equation itself, whose solution is yn equals e to the n times a times y0, which matches this when t is n. So there's a relationship between the differential equation and the difference equation. Got to finish class here. Before we look at what you're doing for number 2, let me also mention something that can help you for number 1 on the linear algebra portion. This, I forgot to mention it earlier, this kind of relationship between A and D mean A and D are what are called similar matrices, when this kind of relationship holds for some invertible matrix P. P could be anything, any invertible matrix, and you would say A and D are similar. That's the definition of similar matrices. That's relevant for number 1 on the linear algebra. Number 1 is what kind of matrices are similar to lambda times the identity matrix? And the answer is, and I even tell you, is it's only similar to itself. And the hint I'll give you there is that any matrix commutes with the identity matrix. In general, matrix multiplication is not commutative, but with the identity matrix it is, and that's a hint. And also the definition of similarity to do number 1. Number 1 is actually a very easy problem if you know what you're doing. To finish class, how do you do number 2? I know I got a lot of complicated ideas in a short amount of time here. Oh, where'd it go? So, okay, we only have time to just outline it here. So you're going to find the matrix exponential. That's going to be with matrix exp in Mathematica, and you can make the output look like a matrix with matrix form. Use your answer to find a formula for the time 1 map. Well, that's just exactly what I was showing you there. It's e to the a times y0. And you just plug in what e to the a is. It's a linear transformation. Y0 is the variable. The initial condition is the variable. I know it's strange, but that's what it is. Then I say find the eigenvalues of eigenvectors and determinant of e to the a. Not a, but e to the a. It's a matrix. Matrix exponential is a matrix. It's got eigenvalues, eigenvectors, and the determinant. You can compute those with Mathematica. So there's no problem computing it. What's more important is there's a relationship between the eigenvalues, eigenvectors, and determinant of e to the a and the eigenvalues, eigenvectors, and determinant of a itself. There's a relationship that comes out in the lectures. Also in the lecture, I talk about the image of a set under the time 1 map and what happens to its area. So S is just some subset of the plane. Maybe you imagine it to be a circle and all the points inside a circle. It's got a certain area. I'm saying it's 10,000. Phi1 of S represents all possible outputs of the time 1 map as you plug in different points in S. What is the image of that circle? Phi1 is a linear transformation. This is stuff we did talk about when we talked about images of linear transformation. What's its area? It comes out in the lecture. I tell you what to do. Okay. Now, again, you could just look at the PowerPoint and maybe you could figure it out from the PowerPoint, but I go into detail in the lecture. Not enough time to really go in depth as much as I wanted to, but keep thinking about it. Okay. Have a good day.